Welcome to our review notes. I'm going to try not to pause too long on these, but I will pause here for a second at each of the beginning of the questions so that you can pause the video and work out the problem if you would like, and then hit play and then go over my explanation. So here we've got the area between the two functions y equals x cubed minus 4x plus 3 and y equals x minus 1. We're going to find the area between these two curves. So I'm going to give you a second to hit pause if you would like. All right, now we're going to work through this problem. So there's a couple things we need to figure out beforehand. We need to figure out where these two functions intersect because that's going to give us our limits of integration. So we're going to take these two functions, set them equal, and we're going to get x squared minus 5x plus 4 is equal to 0. This, of course, gives us a quadratic that is factorable, and we get x is equal to 4 and x is equal to 1. So that's telling us that there is a 1 and that there is a 4. So also we can see from the picture that our linear function is the function that's on top and our quadratic is the function that is on the bottom. So we're going to have the integral from 1 to 4 of x minus 1 minus x squared minus 4 plus 3. If we distribute our minus sign and combine like terms, so yes, I know I'm skipping a step here, so I'm going to let you distribute your minus sign and combine your like terms. So make sure that when you're doing that, that you're distributing that minus sign through, and we should get as our integral negative 1/3 x to the third plus 5/2 x squared minus 4x. And you're going to do this from 1 to 4, and you should get 9/2 or 4.5, and that gives us our answer B. All right, the next question is which of the following integrals will find the area enclosed by these two curves? So again, I'll give you a moment if you would like to hit pause and try this out on your own. All right, so again, the first thing that we need to figure out is where these two functions intersect and, sort of what's going on here. So we're going to take these two and set them equal to each other. And we're going to get, let's see, x squared minus 4. So these intersect at a couple of places, at 0, at 2, and at -2. All right, so let's draw a picture of these because I think that's going to help us. So x to the third, it's going to go through that point, and that point is also going to go through 2, 4, and -2, or -2, 8, excuse me, and 2, 8. It's going to look like that. So there's x cubed. And then our other function, let's see, it's going to have a slope of 4. So it is going to look like this. So we have that situation where for part of our interval, so we are looking for this area plus this area. So the area between those two. And so for a little while, x cubed is going to be the function that's on the top, and then after a while, x cubed is going to be the function that's on the bottom. So we're going to have from -2 to 0, x cubed minus our 4x. But then from 0 to 2, we're going to have 4x minus x cubed. So this answer is actually going to be, now I got to figure out which one it is. It's C, there we go. And if you go ahead and find these integrals, you're going to get 1/4 x to the fourth minus 2x squared from -2 to 0 plus 2x squared minus 1/4 x to the fourth from 0 to 2, and you will end up with 8 altogether. So the area between two curves, it's not taking into account whether you've got some of that area that's above or below the x-axis. It's taking that whole area as positive here. That's why it doesn't zero out. It's because it's looking at that whole area as a positive area. All right, let's take a look at another one here. Which method should we use to find the volume of a solid created by the region enclosed by y equals, or x equals, I can't read anymore, x equals 5y minus y squared. So we've got that graphed over here. Can I just graph that in Desmos to help me? And the y-axis, so closing it off right there, there's the y-axis, and we're going to rotate around the x-axis. So I will give you a second to think about this question. Hit pause. All right, let's finish out our picture here. So if we reflect this over the x-axis, where's that going to be? About in the middle. Trying to kind of draw a reflected picture. It doesn't have to be perfect. I always have to remember that. And this one, because our function is in terms of y, and because we rotated around the x-axis, I'm going to want to use shells because what I want to do is chop up the y-axis versus chopping up the x-axis. So if I come in with that cookie cutter and do the cookie cutting kind of, well, my picture's not perfect, but we'll call it good. So here is our cylinder. And again, remember our thickness is right here on that sort of top edge, and that's going to be dy. So that's telling us that our variable is y. And remember with this one as well, this method, the volume is from, well, we're going to go to c to d, and we're going to have 2 pi y and then g of y dy. So looking at this again, our limits of integration are going to come from the y-axis. So we're going from 0 to 5. So 0 to 5, 2 pi y. So again, why that radius is y. Why is the radius y? Because we're coming out from the x-axis and going to the side of our cylinder. And so that amount, this amount, is a y amount. So our radius is y, and then the height of our cylinder is from the y-axis out until we hit our function. So that's going to be our 5y minus y squared and dy. So there's our integral, and this is absolutely one that we should be able to do, especially when we end up with polynomials. So we get that, or 2 pi 5/3 y to the third minus 1/4 y to the fourth from 0 to 5. And then altogether we get 625 pi over 6. All right, let's take a look at the next question. Oh, so I didn't say it's shells. We want to do shells. All right, so find the volume of the region created by y equals e to the x over 2. So all of that x over 2, that's our exponent. Sorry, the typesetting is not perfect on this. The line y equals 1, x equals 0, and x equals 2. So that's that green shaded in area. And we're going to rotate around the line y equals -1 here. So our region is going to look like, so it's going to be that, and kind of about, not drawing it. There we go. That's a little bit better. So here's our region, and it's going to be like this. It's going to have one of those cavities in the middle. There we go. And so the question is our, first off, are we going to slice this up, or are we going to, use discs? This is one that I'm going to slice up. And part of the reason is that the function that I'm given is in terms of x. Remember, that's not necessarily a problem. We can change that around if needed. But the other reason is because the equation we're given is terms of x, and we are parallel to the x-axis here with what we're rotating around. And so when I go and make my slices, I'm going to slice the x-axis. So that's going to tell me that our variable is going to be x. So again, our formula for this our volume is going to be from A to B, and this has got a cavity, so we're going to have pi times the outer radius squared minus pi times that inner radius squared. And so, let's stop being the obnoxiously loud pink pen there. So our limits of integration, again, our variables x, so they're going to be along the x-axis. It's starting here at 0 and going until we hit 2. So those are going to be from 0 to 2. Our outer radius, and maybe we'll even look at sort of like this biggest washer that we have. So what that's doing is it's this bit here that is our function, plus we've got one more unit there going from the x-axis until we hit that line y equals -1. So our outer radius is our function plus 1. The inner radius, it's the same all the way, whoops, didn't drop big enough, there we go. It's the same all the way down this shape. It is always 2 units. So there is our function that we're going to take the integral of. And if you're doing the integral of this, I would pull that pi out in front, and then we've got e to the x over 2 plus 1 times itself. We'd have to multiply that out minus 4. So if you did want to multiply that out, you would get e to the x plus 2e to the x over 2 plus 2 and then minus 4. So you can combine those like terms to give you a minus, oops, it's not plus 2, it's plus 1. I was doing 1 times 1 and got 2. So those give you minus 3. So your integral ends up being e to the x plus 2, not 2, it's going to be 4. You have to do a substitution, so you've got to change that coefficient there. I'm saving us a little time. And then plugging everything in, you're going to get pi e squared plus 4e minus 11. I definitely wouldn't worry about being able to do an integral like this on the exam. This one's a little long for an exam, particularly with the foiling out of the e, that power of e. It's a little more than probably what we'd want to do on an exam. But for sure, I could give you something like this and have you set it up. The setting it up part of it wasn't bad at all. All right, we've got one more question to take a look at, and that's to find the length of the curve of y equals 9 minus x to the 2/3 to the 3 over 2 from 1 to 27. So I'll give you a second here if you'd like to pause. All right, let's take a look at what this is going to look like. So the arc length of a curve is from the integral from a to b of the square root of 1 plus our function's derivative squared. So remember, I like to do this sort of piece by piece, where I take the derivative of our function here to the 1/2, and then we've got to do times the inside function. Ooh, this is fun. Let's see, what do we end up with? Oh, look at those coefficients. Those are opposites. So we end up with negative x to the negative 1/3. I just want to write that out in front. I don't like those sort of like hanging off the edge there. And that to the 1/2. Okay, that's our derivative. And then our derivative squared. Okay, so remember with this, we're going to square each piece of this because they're being multiplied together. This is being multiplied. So we're going to square that negative 1/3, negative x to the 1/3. Again, we can read today. To the 1/2 squared. Okay, so that x is going to end up being positive x to the 2/3. Oh, and I lost my negative there. Sorry about that. That should be positive x to the negative 2/3. Ooh, okay, there we go. And then this squared and that square root cancel out, and we're just left with 9 minus x to the 2/3. So if you would like to, you can rewrite this like that. We can divide by that negative exponent. And if you'd like to go a little further with this, you absolutely can. I'm totally fine with this one the way that it is right here. It's kind of ugly as it is. You could also think about distributing this through, and then that would give you 9 over x to the 2/3, and then actually minus 1. So either way is fine. It's kind of up to you. So then that's what we're going to take the square root of. So the length of our curve is going to be from 1 to 27, the square root of 1 plus, I think I'm going to use this guy right here that we have written, minus 1 dx, because then the 1's cancel. Ooh, that's nice. So integral from 1 to 27, and we just have the square root of 9x to the negative 2/3 dx. And then actually what you can do is simplify this a little bit, because the square root of 9 is 3, and then you've got x to the negative 2/3 to the 1/2. So this is the integral from 1 to 27 of 3x to the negative 1/3. So that's actually not so bad at all. And we can take that integral, we'll go over here, integral from 1 to 27, 3 to the negative 1/3 dx, and we get 3 times 3 over 2 x to the negative 2/3 from 1 to 27. So you actually end up with 9 halves there. But overall, once you do that, you end up with 36.